Hi, during today's session we're going to talk about velocity and acceleration. Hopefully you've already watched the other teacher's video on it, so you have a pretty decent understanding of this. Today with me, we're just going to talk about all the concepts that will most likely appear on your tests. So we're really going to focus in on the key things you need to know to be successful in this next assessment. So technically this lesson is normally accompanied by a video. The video is horrible quality through the recording, so we're just going to ignore the video, which really isn't that great anyway, and just kind of speed through the notes so we're as speedy as we can be. So if we think about average velocity, we've talked a lot about average velocity in this class. Average velocity was the very first thing we did on the very first lesson with limits. Average velocity, remember, is the distance traveled divided by time. So distance divided by time. So for example, if I travel 200 miles in 4 hours, my average speed is 50 miles per hour. Now that's just my average velocity. I'm not going 50 miles an hour the whole time. Sometimes I might be traveling 30 miles an hour, and sometimes I might be traveling 70 miles an hour. Sometimes I might be traveling 45 miles an hour, and sometimes I might be traveling 65 miles an hour. I might never actually drive 50 miles an hour. I might just hit 50 miles an hour at one point to get to the speed I'm actually going. An average velocity is great, but it doesn't tell us very much because it's just telling us an average, doesn't tell us any specific times. And that's where we need the instantaneous velocities. So in order to find that, we have to start with our position function. So position function is represented by s of t or p of t. And the position function represents the position along a line with respect to time. It kind of tells us how far away from 0 we are. Position tells us where we're located. So the derivative of the position function, that's the instantaneous velocity. And that's what we're really looking for when we want to know the velocity at a certain moment in time. So that's the instantaneous velocity, and we call that the velocity function. So to find the velocity function, we simply find the derivative of a position function, or we call it just v of t for velocity. And the other guy that was teaching his lesson also touched on this. So velocity is when we have direction involved. So if I'm going forward 5 miles an hour, then the velocity is positive. But if I need to turn around and go back, velocity is negative. So velocity always shows a direction. Speed does not. If I'm going, so velocity, if I'm going forward 20 miles an hour, it tells me that. But if I'm going backwards, it will be negative. And I'm going to make that slower because hopefully you're not backing up at 20 miles an hour. So velocity has a direction. Speed does not. It doesn't matter if you're backing up or going forward, your speedometer in your car reads a positive number. So speed is always the absolute value of velocity. You wouldn't say I'm traveling negative 5 miles per hour. That's silly. You're traveling 5 miles an hour. So we also know that the derivative of the velocity function is the instantaneous acceleration. So that tells us how much we're accelerating at a given time. And word that a different way, acceleration is the rate of change of velocity. So it's just showing us how the velocity is changing. It is represented as a of t, or it's the derivative of velocity, or it's the second derivative of the position. Now, acceleration tells us how the speed is changing or the velocity is changing. So for example, if I'm not speeding up, my acceleration is 0. If I am speeding up, then my acceleration is positive. It's how my velocity is changing. So before we move on, let's just summarize all this. We know the position function is s of t, or sometimes p of t. The velocity function would be represented by v of t, or it's the derivative of that position function. And the acceleration function is the first derivative of the velocity function, or the second derivative of the position function. Some students last year remembered PVA. I don't know. They just use that as their mnemonic. I don't think that's extremely helpful, but maybe you can come up with something better. So we know that if the velocity is greater than 0, the position is increasing with time. If the velocity is less than 0, the position is decreasing. If the velocity equals 0, then the position is constant. That means our object is not moving, it's stopped. If the acceleration is greater than 0, then the velocity is increasing. If the acceleration is less than 0, then the velocity is decreasing. And if the acceleration equals 0, then the velocity is constant. Let's talk about this one for just a second. A constant velocity does not mean an object is not moving. It just means that the velocity is not changing. So an example of a constant velocity would be when you're driving down 95, you get up to 70 miles per hour and you hit cruise control. At that moment in time, once you hit cruise control, your velocity is constant. The speed's not changing. So you have an acceleration of 0. It doesn't mean your car is not moving, it just means that the velocity is not changing. So when the acceleration is greater than 0, this would be like when you're getting on 95, and you have to speed up kind of quickly to when you have to speed up kind of quickly to get on the ramp, and then the acceleration is less than 0, that would be like when you see the cop and you slam on the brakes a little bit because your speed's decreasing, your velocity is going down. So those are changing, and that's how you think about acceleration. Alright, so now we're going to look at an example. And you're supposed to watch a video clip of this example, but this is the path of a guy named Flip, and he's this crazy dude that's delivering some goods for his father's business. And without watching the video, let's just look at this, and we're going to look at it in the calculator. And if you look, I've already magically plugged this function into the calculator. But I also took the time to change my window, or I'm going to take the time to change my window from 0 to 5, and I'm going to make my y max just 10, the normal 10. Mine got changed for something else. So we know, well, you were supposed to know that the domain of this function was kind of given to you. The domain of this function is 0 to 5. So I'll explain more about the situation after we graph it and see what it looks like. So if we look at the graph, there's the function. Clearly it's a cubic function. And if we look at the table, there, let's pull up 0. There's our handy table. And I'm not going to take the time to recopy my table, but there's the table. So we know at time 0, his position was 0. At time 1, his position was 4. At time 2, his position was 2. At time 3, his position was 0. At time 4, his position was 4. And then he went up to 20. So this was our lovely function, and I actually just did a decent job of graphing that compared to what I've done with some of these other ones. But I'm going to cheat, and I'm just going to pull my graph over so I have a nice smooth graph. So let me tell you about the situation that you were supposed to see in the video. So what happened here was, this happens to me like every day of my life. I start at my house, I walk out the door, I get a little bit away from the house. In this case it's 4, let's call it feet, but It could be 4 miles, or it could be 4 whatever. Let's call it feet in this problem. Get 4 feet away from my house, and I realize I forgot my phone, or I realize I forgot something. And I have to turn back around and go back inside my house. So my position becomes 0 again. I'm back inside my house, and then I move away from the house again. I finally get to go on my way once I have my phone or whatever I've forgotten. So that's really the whole situation that you needed to know. You need to know that the position is in feet and t is seconds. And the problem told us that, but you didn't get to see that. Just disadvantage of this. Well, from that position function, we can easily find our velocity function, because hopefully you've realized that the velocity is the derivative of the position. So we're just going to find the derivative of that, which is 3t squared minus 12t plus 9. And if I wanted to know the velocity at time 4, I would simply plug in 4. And if I plug in 4, what do I get? Let's see. 3 times 16 minus 48 plus 9. 3 times 16 is 48, minus 48 plus 9 should be 9. Let's just double check that before I go on and do it wrong. So yeah, so that equals 9. And because this is a velocity, we want to make sure that we write it in terms of our measurements. Now, I didn't give you measurements this time, I don't think. So let's assume, because it was only in 5 seconds, that this was 9 feet per second. Now, it didn't tell us that, but we're assuming it just for the point of this. If it gives you the distance and time, you have to write it. Otherwise, it will be wrong. A lot of times on the AP test, that's one whole point, is just writing your labels. Well, the acceleration function will also be easy. The acceleration is the derivative of velocity, which is the second derivative of the position. So we already know our velocity function. It's right here. So if we find the derivative of that, we get 6t minus 12. And we can do this one easy. 4, we have 6 times 4 minus 12, which gives us 12. We're doing this with respect to time, so 12 feet per second squared. So acceleration always has squared on the bottom, because remember, we're finding the derivative of time again, but only with respect to time, not with respect to the distance. So now we're going to graph these functions. So now it wants us to graph the velocity function, so I dragged the velocity function over so we could see it. And I then went to my calculator and I plugged it in. And of course, if we hit graph, we have a parabola, which makes sense because we had a cubic function, and the derivative of a cubic function is a parabola. So of course, we can go to our second table and get some points to graph. We have 0, 9. And of course, I didn't keep that up. 0, 9, 1, 0, 2, negative 3, 3, 0, and 4, 9. And of course, that would continue to go positive, and we would do the best job ever. That was the worst job ever. The best job ever connecting that into a beautiful parabola. And I knew that was going to happen, so I'm all prepared. We're going to hit graph and cheat. So you would have a beautiful parabola that looks just like that. Alright, so then hopefully remember that the speed is the absolute value of the velocity. So to graph that, we do the exact same thing, but anytime I have a negative value, I'm going to make it positive. So we still have 0, 9, we still have 1, 0, but now I have 2 positive 3. 3, 0, and 4, positive 9. And I can do a decent, well, that's actually pretty stinking decent, folks. Wow, that's amazing. But if I wanted to do this in the calculator, I could actually use the absolute value function, So if we came down here and did second math, try that again, second math, no, regular math, num, ABS, and type in the exact same equation that we had before. So 3x squared minus 12x plus 9. And if I hit graph, you can see it's the exact same thing. I'm going to go back and turn this one off, so that way I only see that speed function. And there we go. So there's our beautiful speed function. Of course, I'm going to cheat and drag that in, although my diagram really wasn't so bad this time. All right. So now we know our acceleration function was 6t minus 12. So of course that's just the equation of a line. So we can simply go 6t minus 12. So I'm going to need to count by something other than ones here. So if I count by 2's here, I want to keep counting by 1's here though. So this is still 1. So if I start at negative 12, 2, 4, 6, 8, 10, 12, I'm going up 6 over 1, up 6 over 1, up 6 over 1, up 6 over 1, up 6 over 1. Because remember, each of these count as 2. And then I'm going to draw a beautiful line. I'm not even going to try to do that because I have this lovely line feature. That did an awesome job for me. I can even make it red. Maybe. Now it's beautiful. It looks perfect. Alright. So now we're going to answer all these questions. And I kind of was proactive and I put all of these down for us. So I have the graphs with my lovely drawings. So we have all these graphs, so let's look at the questions. It says, when is Flip going away from home? So think about that. That's kind of a velocity question because velocity tells us direction. So because it's saying velocity, because it's saying direction, we think velocity there. Now think about it, going away from home. That means moving in a positive direction. So anytime the velocity is positive, so it's positive from 0 to 1, it's also positive from 3, and then we're only going to 5 here, so from 3 to 5. I'm going to put a bracket there, but know the parentheses and brackets here are not a huge deal. I'm putting a bracket at 5 because at 5 he's continuing to move away from home. However, at 1 and 3, he's changing direction. So at 1 is when he realizes, whoops, I forgot those dumplings, and he turns back around and goes back towards home. So likewise, between 1 and 3, that's when he's going back to his house. Now, if you go over here and look, you can kind of see this also. From 0 to 1, his distance from home is getting larger. But then from 1 to 3, he's getting closer to home. He's going back towards the house. And then from 3 to 5, or 3 to infinity, he's going away again. So this 5 is a little bit questionable. I'm only using 5 because the problem says we're using it for 5 seconds. But the 5 really could possibly be an infinity there. So, now when is he changing directions? When does it switch? So, we know at 1, he realizes, oh no, I forgot the dumplings. And then again, once he gets back home, he gets the dumplings, and then he turns around again. And at 3, at those 2 times, he switched directions. So at 3, he leaves the house again. Now, when is the acceleration positive? Well, this one's pretty obviously going to use the acceleration function that tells us. So if we look, the acceleration is positive when it's greater than 0. So from 2 to 5, or from 2 to infinity. Once again, I used the bracket there because at 5 it is positive. I did not use the bracket at the 2 though, because at 2 it's technically 0. It's not technically a positive number. Now, sometimes the AP people use a different definition. They say that a number is positive if it's not negative. So sometimes they will put 2 in brackets also, but they'll never trick you. They'll never put some parentheses and some brackets in hopes that you know which one to use. They don't play that game. So if they have a bracket here, it still could be correct because they're using a definition for positive. That means anything that's positive is not negative. So 0 is technically not negative, so it can be considered a positive number. However, in my mind, 0 is neither positive or negative, so that's why I use a parenthesis. Alright, when is Flip's acceleration negative? Well, it's negative from 0. It's clearly negative at 0. And then to 2. So when is his speed increasing? So for speed increasing, we need the speed function. I'm going to just drag it down here so it's in my window. Oh, maybe I'm not going to do that. So speed increasing is anytime the speed is going up. So you see the speed's going up from 1 to 2. And also from 3 to 5. Or from 3 to infinity, depending on what you think that endpoint is. And then the last question says, well, where is it decreasing? Well, clearly his speed is going down from 0 to 1, and then again from 2 to 3. So that's what we would write, 0 to 1, and 2 to 3. So that's really the basis of a lot of the problems we're going to do, these graphs. Alright, so let's look at our second example. This example is about an egg being thrown into the air. It's using this equation as its position function. So just imagine you have an egg that's being thrown up into the air, and of course that's going to take the path of a parabola. So before we do anything else, let's go ahead and plug this into our calculator. So look at y equals, it's magically there. And then I looked at my table to see what kind of values I needed. And if you notice, this one's getting really, really tall. The y value goes all the way up to 150. And we can see that it's going to land on the ground somewhere between 6 and 7 feet. So when I set my window, I said x should be between 0 and 10. And my y should be between, well, really it could be 0 and 150. Because it can't go below the ground, and I know it's going to 150. Maybe to be safe, we should make it a little bit more than 150, maybe 175. So if I look at my beautiful graph, there it is. And I'm going to go ahead and pull my table out too, so I have that. So once again, this is the height that an egg's being thrown up into the air, and let's say that it's in feet. Let's say that the distance is being measured in feet, and the time, of course, is being measured in seconds. So if we want to know how high the egg is after 2 seconds, we would simply plug 2 into the position function, because height is a position. So we plug 2 into that s function, and of course we already have it. So that's 134, let's say, feet. And then 4 seconds, there's 4, it's also 134 seconds. So if you think about this on the parabola, 2 has the same height as 4. So we have a parabola, it's going up at 2 seconds. So at 2 seconds, the velocity will be positive because it's going up, but at 4 seconds, it's coming back down, so the velocity will be negative. All right. Now, well, if we look at our table, can we find it? So when is the position back at 0? Well, I know it's between 6 and 7 seconds, but I don't know exactly where. So if I have a calculator, I would simply find my 0. So I would go back out to trace. Let's change our window up some for this problem. So I know I need my y max to be much higher. I know I saw 134. What else do I see? 150 looks like my highest y value. So I'm going to make my y max, let's say, 175. So now let's look at this graph. Do I get a better picture of this egg? Oh, it's pretty close, but I need to make that window a little bit larger. Let's make that 10. So let's see what happens. Not 110, just 10. Alright. So there's our graph, so you can see it hitting the ground. So second trace 0. And it's hitting the ground between, what did we say, 6 and 7? So let's just hit enter there. On the left-hand side, we go to the right-hand side, we hit enter. It's actually 6.06. So how long does it take the egg to hit the ground? Oh, about 6 seconds, or 6.06 seconds. Now that's well if you have a calculator. If you don't have a calculator, you're going to have to use that good old quadratic formula. And of course that'll be fun. So opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. Of course I've made this hard to read now. So when I do the inside of that square root, 96 squared minus 4 times negative 16 times 6, I get 9,600. Wow. So I have negative 96 plus or minus the square root of 9,600 all over negative 32. The square root of that would be 97.97. So I have negative 97, or no, excuse me, negative 96 plus or minus the square root, or plus or minus 97.9796 all over negative 32. You can do both of these. If you do negative 96 plus 97.979, you'll get 1.979 divided by negative 32 is a negative number. Doesn't really matter what that negative number is. Time cannot be negative, so that one won't work. But if you do negative 96 minus 97.979, hit enter, you'll have negative 193.979 divided by negative 32. Hopefully we get, sure enough, 6.06 seconds. So if you can use the calculator or use the calculator every single time, you never have to do the quadratic formula. But if you can't use the calculator, you're going to have to use the quadratic formula in there. So then it says, well, when does the egg reach its highest point? Well, of course, you can know that it's symmetric. So if 134 and 134 is on both sides, then the vertex has to be 150. So it has to hit at 3 seconds. That's the simple way of doing it. If you have a calculator, of course you could use your maximum feature, second trace maximum, and we can go to the left-hand side. Well, 2 seconds is on the left-hand side. We can go to the right-hand side, 4 seconds is on the right-hand side, and press enter. And sure enough, the maximum happens at 3,150. But that's still really using algebra. Instead, to use calculus, we know that it's going to hit the highest point, think about that, when the derivative is 0. So if we found the derivative of this function, which we know is negative 32t plus 96, and found what made that 0, so what makes that value 0? Let me erase some of this now. Well, maybe. So if we find out what makes that 0, so 0 equals negative 32 plus 96, we subtract 96 from both sides, divide by negative 32. Sure enough, t equals 3. So the maximum happens at 3 seconds. And then how high does it go? Well, we already know that that's 150 feet. But if we don't have the calculator, what function do we need for height? So height is a position, so we're going to have to use the position function. So we had to use the derivative to find the time, and now we'll plug that time into our position function. And when we plug 3 into the position function, you can actually plug it in, so, you know, negative 16 times 3 squared plus 96 times 3 plus 6. Or you can just look at the table. We already know that when it's 3, you get 150 feet. I think feet. Feet seems really big though, doesn't it? If it's a chicken throwing an egg up in the air. So feet's questionable. I don't remember what the problem said, but feet seems huge. 150 feet for an egg? I don't know. It is math. It is a math problem though that was probably just randomly made up. Alright, so we have 2 quick questions to look at and we'll be done. So this should be in your notes still. The accompanying figure shows the velocity of a function moving on a coordinate line. Let me go ahead and make this a little bigger, or a little smaller. Oh, I guess I was recording that whole time. I'm sorry. So I made it smaller. So anyway, this is the velocity function. So remember, what does velocity show? Velocity shows direction. So this is showing a positive velocity means a positive direction. So this says, when is the particle moving forward? So when does it have a positive velocity? So forward would be between 0 and 1. Where else is it positive? Between 5 and 7. Is there any other place where it's positive? Not so much. Where does it move backward? Well, that would be when it has a negative velocity. So this is where the velocity is negative. So between 1 and 5, it's negative. Now remember how the next thing says speed up and slow down. So both of those are speeds. So in order for us to look at speeds, we have to do the absolute value. So any of these functions where it's negative, I need to draw it in the positive direction. So this point that's down here is going to flip up here, and this point that's down here is going to flip up here. And then my new graph is really wow, that was awful. Give me a second. I'm going to go ahead and try to clean that up a little bit. Okay, that's as good as it's going to get, but know that this piece right in here should really look exactly like this piece in here, just a reflection. And I did a bad job with that, but I only have this slate, so I can't really use my pencil. So anyway, it's speeding up when it's going up. So it's speeding up from 1 to 2. It's speeding up from 5 to 6. So whenever the speed function is going up. Now it's speeding down. When is it going down? From 0 to 1. And it's going down from 3 to 5. And it looks like it's also going down from 6 to 7. So those are all the down ones. So that's question A. Question B says, when is the particle's acceleration positive, negative, and 0? So acceleration would be when the velocity is increasing, because remember the acceleration is the derivative of velocity. So basically whenever the when it's positive, that's when the velocity has a positive slope, because velocity is acceleration is the derivative of velocity, so we know that's whenever it has a positive slope. So if we think about positive slope, well, this function has a positive slope between 3 and 6. When is the particle's acceleration negative? Well, negative would be when the slope is negative. So we have a negative slope between 0 and 2, and between 6 and 7. And then it also says find where it's 0. So 0 means that it is not moving. So it is not moving between 2 and 3, and between 7 and 9. When does the particle move at its greatest speed? So basically, if we go back to that graph that I did a lovely job, hey, this time it actually looks decent. If I go back to that graph, when is the speed the greatest? So it's at its greatest speed when the speed is at its highest point. So that looks like t equals 0. And also between 2 and 3. So it's at its greatest speed when t is 0 because it's at its highest point there. And also between 2 and 3. That's when the speed reaches its highest point. And then when does the particle stand still for more than an instant? So think about what standing still means. Standing still means that the velocity will equal 0. So where does the velocity equal 0? We have this point, we have this point, and we have all of these points. So if the question is where does it stand still for more than an instant, our only answer would be between 7 and 9. Where is the velocity 0? Between 7 and 9. Okay. Alright, so this is the last problem. I know these notes have been long, and I appreciate you hanging in there with me. So, if we look at this, we're going to talk about instantaneous rate of change. And if you think back to Algebra 1, your Algebra 1 teacher just told you rate of change always means slope. And now that we're in calculus, we know slope means derivative. So anytime it says find the instantaneous rate of change, we're going to find the derivative. So it says find the rate of change of the area of a circle with respect to its radius r. So hopefully you know the area of a circle is pi r squared. So that would be the original equation. But if we need to find the rate of change of the area with respect to the radius r, so now we're finding the derivative with respect to r. So we're finding the derivative of the function just using r instead of x is really all this means. So the derivative of a with respect to r, well, let's see. We bring the 2 in front, so it's 2 pi r. And we found it with respect to r, so that's it. So it's just finding the derivative of the function using the power rule. I maybe used weird notation on you there. We'll talk about this notation more when I come back, but really you're just finding the derivative. So then part B says evaluate the rate of change of A when r is 5. Easy peasy, I just plug in 5. So 2 pi times 5, which I'm going to call 10 pi, and I'm not going to do anything else with that. And then it says do the same thing at 10. Well, that's not bad. 2 pi times 10 is 20 pi. And then, last but not least, if r is measured in inches and a is measured in square inches, what units would be appropriate for dA dr? So, our area is square inches, so we would be measuring in inches squared per inch. So what this is saying, how does the area, which is inches squared, change for each inch of the radius? So inches squared per inch. Alright, I tried to make your assignment really small for this section because the notes were really long, and we're going to spend a lot of time on this section next class. So the goal was really just to give you a good basic understanding of this section so we can spend some time on it next time, really getting into it and practicing it. Have a good weekend. I hope you have lots of time to get everything caught up.